This lecture will provide solutions for selected homework problems, covering the chapters after the midterm. If you have a question for other homework problems, you can contact either the TA or myself on Teams. 20.3. A uranium-235 filled light water reactor is operating at a power level of 250 megawatt electric power. Control rods are removed to give a reactivity of 0.0005. Noting that this is much less than the beta. Calculate the time required to go to a power of 300 megawatt E, neglecting any temperature feedback. So this is a transient problem. And first, based on the fact that this reactivity is much smaller than the beta. The beta is 0.0065 for this uranium-235 light water reactor. And we have this reactor period equation. And if the delta K or the reactivity, the delta K and the reactivity rho, they are interchangeable, so they have the same meaning. If this delta K is much smaller than the beta, we are going to use the first equation. Otherwise, we use the second equation. For this problem, we use the first equation. Therefore, we are going to calculate the T reactor period first. So the reactor period T is equal to beta tau over rho. The beta and tau are both constant for certain fuel, and for 235, this value is 0.0065, and tau has been calculated as 12.7 seconds. So we use the beta, which has no unit, times the tau, then divided by the reactivity or the delta K, which is also no unit. We have the reactor period. Then with the reactor period, we have the reactor power Pt is equal to P0 times this exponential function. And this P can be either thermal power or the electrical power, because the electrical power is proportional to the thermal power. Then we are going to substitute all those values into this equation. So we have 300 megawatt for the final power, 250 megawatt as the initial power, times this exponential factor. This T is the duration of time for 250 megawatt to reach 300 megawatt. Then we solve this equation, then the T will be equal to 30 seconds. Means that after 30 seconds, this reactor will go from 250 megawatt to 300 megawatt. 20.13. A reactor is loaded with 90,000 kilograms of uranium at a 3 weight percentage of uranium-235. It operates for a year at 75% of its rated 3,000 megawatt thermal capacity. Apply the rule of thumb 1.3 gram per megawatt a day to find the consumption of 235. And also, another question is what is the final enrichment of the fuel? So from this problem, we know that to produce 1 megawatt a day of thermal heat, it will consume 1.3 gram of the 235. Therefore, first we need to calculate how much heat is produced over a year. We have the reactor power times the capacity factor. That will be your average thermal power. Then times the number of days in 1 year. So we have a megawatt times the day, we get the unit for megawatt a day. Then times 1.3 gram per megawatt a day. So we get the number of gram. And we convert the gram to kilogram. That is the mass of 235 consumed. So again, the power, average power. So rated power times the capacity factor, you get the average actual power, then times the duration of time in the unit of days. So we get a megawatt day. The number of megawatt day times 1.3 gram per megawatt day, we get the number of grams of the 235 burned, consumed. And then we convert it to kilogram. Okay. Next, what is the final enrichment of this fuel? So the enrichment definition is the uranium-235 mass over total uranium mass. Okay, uranium-235 mass over total uranium mass. And in the numerator, we need to calculate the final mass of 235. So we use the initial mass, 90,000 kilogram times 3%. This is weight percentage. That is the initial 235 mass minus the 235 consumed. That is the remaining 235. Okay, remaining 235 over the total amount of uranium after 1 year. So the initial total uranium is 90,000 kilogram. Then subtract the 235 consumed, because if the 235 is consumed, then it is no longer uranium, and we need to subtract this mass from the uranium inventory. So we use the initial total uranium minus the 235 consumed. That is the total uranium left inside this core. Then the result will be 1.84%. This is weight percentage. So the 235 enrichment is reduced from 3% to 1.84% after 1 year of operation. Next chapter. Expand the PRA for figure 21.6a by considering the possibility that the tank holding the water supply fails. Then A, draw the fault tree. Then B, compute the probability that the top event occurs if the probability the tank fails is 10 to -5. Follow the example 21.3, let the event probability PA is equal to PB is equal to 10 to -3 for pump failure, and PC is equal to 10 to -4 for valve failure, and calculate the probability. So go to the figure 21.6a. It is shown here. In the textbook and also the class example, we only consider the pump and the valve fail. We didn't consider the water supply failure. And next, we are going to include one more basic event to determine the possibility for no water flow to the reactor. So the solution is shown here. Okay, solution is shown here. And you see that water supply pumps and the valves, they are serial connection. Therefore, their relationship is OR. Okay, if there's no water supply, or all pumps fail, or valve fail, it will cause the reactor fail. So any one of these fail will cause the no water to reactor. Therefore, after this top event, no flow of water to reactor, we have this OR gate. Okay, pay attention how this OR gate is drawn. So you have a pointy on the top, and then you have a curve at the bottom. Then you have three events. Okay, three events. One is the water tank empty. Okay, water tank empty. So here we use the W to denote that. And valve fail to close. Okay, valve fail to close, and we follow this notation from the textbook. We use the C. Another one is the pump failure. Okay, the pump as a whole system, it contains two subsystems. So that is pump 1 and pump 2. Yeah, pump 1 and pump 2. And to have no flow to this valve, we need to make both pump to fail. Okay, make both pumps to fail. Therefore, below this one we have an AND gate. Okay, we have an AND gate. And this AND gate will have two basic events. That is pump 1 fail and pump 2 fail. And this concludes the fault tree. Okay, fault tree. So we just have one more of this valve failed closed attached to this OR gate. Okay, so this is the only difference. Then we calculate the failure rate. Okay, probability of no flow to reactor. So that is top event PT is equal to PC plus W plus F because they are OR relation. Okay, we have bracket then C plus W plus F. Okay. Then it is approximated by PC plus PW plus PF. This is due to the rare event approximation. Okay. If you want, you can also use the full equation. It will not change the result that much. Then PC and PW are given. Okay, so PC is 10 to negative 4, then PW is 10 to negative 5. Okay, 10 to negative 5. Then PF is unknown because PF has another two branches. So PF is equal to PA times B. Okay, PA times B. This is AND gate. So for the AND, that is A times B. Then we further expand this PA times B will be PA times PB. Okay, PC plus PW plus PA times PB. From here, we can substitute all those numerical values. Okay, PC, that is valve fail, which is 10 to negative 4. Okay, 10 to negative 4. PW is 10 to negative 5. And P and PB, they are both 10 to negative 3. Then we get the result, 1.11 times 10 to negative 4. This will conclude this problem. 21.10. When a large positive reactivity is added to a fast reactor assembly, the power rises to a peak value and then drops, crossing the initial power level. In this response, which is the result of a negative temperature feedback, the times required for the rise and fall are about the same. If the neutron lifetime is 4 times 10 to negative 6 seconds, what would be the approximate duration of an energy pulse resulting from a reactivity of 0.0165? If the peak power is 1,000 times the initial power, okay, then the beta is equal to this value. So in general, the question is that what would be the approximate duration of the energy pulse during resulting from a reactivity of this value? So means that we'd like to determine the time needed from here until here. Okay, from here until here. We also know that the time for increasing the power is equal to the time needed for the power to drop. Therefore, we just need to calculate 1/2 of this time. That is enough. Okay, that's enough. So the power increase is due to the reactor period. Okay, due to the change of this reactivity. So we need to calculate the reactor period as well. So for reactor period, we have this formula. Okay, again, the same formula. But for this problem, it is a fast reactor. And the reactivity for delta K is much larger than the beta. Okay, it's larger than the beta. You can see that this delta K, which is 0.0165, is larger than the beta that is equal to 0.0065. Then from this equation, we know that we need to use the second formula. Okay, second formula. And for the second formula, we have the LP, that is neutron lifetime, which is given by the problem. That is 4 times 10 to negative 6. That is the prompt neutron lifetime. Okay, prompt neutron lifetime. And the delta K is given as 0.0165. Beta T is also given as 0.0065. Okay. So we throw out the numbers into this formula, we calculate the T, that is 0.0004 seconds. Okay. Then again, the reactor power is going to increase exponentially. Okay, increase exponentially. And we move the P0 to the left-hand side. Okay, move the P0 to the left-hand side. So PT is 1,000 times of the initial power. So the final power PT over the initial power P0 is equal to 1,000. Then it's equal to exponential function T over 0.0004, which was calculated here. Now we solve this equation, we get the T that is equal to 2.76 times 10 to negative 3 seconds. Okay. So this is the time needed for the power increasing. And the problem asks for the entire pulse duration. So that is 2t. Okay, that's 2t. Then just twice of this t, we get 5.5 times 10 to negative 3 seconds. That will be the final answer. Problem 21.12. On a conservative basis, calculate the total decay heat produced during the first 2.5 hours of the 3 Mile Island 2 accident. Okay, we only solve for the problem A. We also know that the TMI2 electric power is 880 megawatt E with efficiency of 1/3. First, we convert the electric power to thermal power. Because efficiency is 1/3, we only need to multiply the electric power by 3, or use the electric power to divide this efficiency. Okay, 880 divide 1/3, so times 3, we get the thermal power. Then next, we calculate the total heat produced within the first 2.5 hours. Okay. And the power times the time will be the heat. And for the decay heat, for the decay heat power, it is a function of time. Therefore, we need to use the integration. Okay, we integrate the power, we can get the total heat. Therefore, we integrate this P from 0 up to 2.5 hours. Okay. Then we have the P equation. Okay. The decay heat power equation, that is initial power P0, which is constant, we just calculated here, times 0.07 times tau to negative 0.2, then d tau. Okay. Here, the next will be your calculus 1 knowledge. Okay, how to perform the integration. And the result will be this one. Okay, will be this one. Then the tau will be evaluated from 0 to 2.5. Okay, from 0 to 2.5 hours. Make sure that you use the seconds, okay, because this is the empirical formula, and this time will take the second as its unit. So everything here, they are either the coefficient from the equation or some coefficient from the integration as 0.8. And this 2640 is the thermal power. Okay, thermal power. Unit is megawatt. So later the result will be megajoule. And we evaluate the tau from 2.5 hours, okay, 2.5 times number of seconds, minus the 0 seconds, okay, minus until the 0 seconds. Then use your calculator, you can calculate this final result in the unit of megajoule. So the unit will follow this P0 unit. Here we use the megawatt, so the result is megajoule. You can further convert it to gigajoule. The only difference between this problem and the class example is that for the class example, we integrate this equation from some time until another time. For this one, we integrate from 0 until 2.5 hours. Okay, that is the only difference. Problem 22.9. The Savannah had a range of 560,000 kilometers at a speed of 20 knots. For a single fuel loading, compute the uranium-235 mass consumed for this specification. B. Calculate the volume of diesel fuel required to provide the same power if a barrel of oil release 5.8 times 10 to 6 BTU, and the reactor thermal power is 74 megawatt thermal. To calculate the total amount of 235 consumed, we need to know the total amount of the heat produced. And we have the reactor thermal power. Then the other missing information is the duration of the time. Okay, duration of time. So this one, we consider this one is traveling this amount of distance at this speed. Okay, at this speed. So we have the total distance. We have the speed. Then we can also have the time, traveling time. Okay. So traveling time t is equal to the total distance over the speed. We convert the speed 20 knots to kilometer per hour, okay, to kph. Then we get this number of hours, okay, this number of hours. Then the total heat in the unit of megawatt a day will be the power in megawatt times the time in days. Okay. So 74 megawatt thermal times the total number of hours divided by 24 hours per day. So that is number of days. Then we get this number of megawatt a day. Okay. To be more specific, it's megawatt thermal day. We also know that this to produce 1 megawatt a day, it will consume 1.3 gram of 235. Therefore, we use this megawatt a day times this factor. So we get this number of 235 that is consumed. That is 60.6 kilogram. Okay. It is not a very large mass. Then, if we use the oil to produce the same amount of heat or produce same amount of energy, then what will be the number of barrels, so that we can make a comparison and appreciate the advantage of the nuclear power. So we use the 74 megawatt thermal, okay, then times the number of hours. So this is traveling time. So we use the watt times the seconds. So we get joule. Okay. So power times the duration of time, we get the total heat. And we use the SI unit so that in the numerator the unit is joule. Okay, joule. Then divide the energy released per barrel. Okay, energy released per barrel. So that is 5.8 times 10 to 6 BTU times this factor. So we convert the BTU to the to joule, okay, to joule. So this is the number of joules per barrel. Then we get a number of barrels, and this is the number of barrels. So this is a huge amount of volumes and masses for the fuel. If this vessel is powered by the conventional chemical fuel. Traces of plutonium remain in certain waste solutions. If the initial concentration of 239 in water were 100 parts per million, and this is the mass ratio, find how much of the water would have to be evaporated to make the solution critical, neglecting neutron leakage as if the container were very large. We know the cross-section for hydrogen and plutonium. So this problem means that the neutron will be absorbed by both water, the hydrogen in water, and also the plutonium. If you have a large quantity of the hydrogen, it will absorb too many neutrons, and the solution will not be critical because there are not enough neutrons absorbed by plutonium. Then if you begin removing the water, then eventually more and more neutrons can be absorbed by the plutonium. Then eventually you are going to have a critical solution. Therefore, first we need to determine what is the final atomic ratio between the hydrogen and the plutonium, so that it will make the solution critical. We also know that this solution is very large. Therefore, we can use the K-infinity equation. Okay, K-infinity equation. So the K-infinity is equal to mu times sigma f over sigma a. Okay. So for the fission, only the plutonium can do the fission. Okay. So in the numerator, just the mu and sigma f for the plutonium. But for the sigma a, we have both plutonium and also the hydrogen. So we have a sigma plutonium absorption plus absorption cross-section for the hydrogen. Okay. Here we set the x as the ratio of hydrogen atom over the plutonium atom. Okay, we set the x as the hydrogen atom over the plutonium atom. So this is atomic fraction. Okay, atomic fraction. So we'll see that if this x is very large, then you have the subcritical solution. Then if this x is low enough, then this K-infinity is going to be increased. Okay, we set this K-infinity to be 1, and we solve the x. Okay, solve the x with this value. This one means that when the NH over N plutonium is equal to this value, it will reach the critical. Then if this value is even reduced, then it will go to supercritical. Okay, supercritical. So this is the atomic ratio. Okay, atomic ratio. Then for this problem, this concentration of plutonium is given as ppm for the mass. Okay, ppm for the mass. Therefore, we need to calculate what is the new ppm for this plutonium. Then we use the definition for this concentration. So we have plutonium mass over the water mass. Okay. So for 1 part of for 1 mole of plutonium, we have a 3445 water. Okay. For 3445 hydrogen, and each H2O molecule contains 2 hydrogen atoms. So we need to use this value to divide by 2. So that is the molar molecular ratio. Okay, that is molecular ratio. So this is number of moles. So for 1 mole of plutonium, we have this number of moles for the water, then times the mass of water. Okay, mass of water. We get this value. Okay, this value, and then we use this value to multiply a million. Okay, multiply a million. So that is 7708 because this is parts per million. So that is this is a new ppm. It means that we need to increase the plutonium from 100 ppm to 700 ppm. Okay, then the amount of water evaporated will be calculated by this value. Okay, so 100 over 7708, that is the ppm ratio. Then we use 1 minus this value, that is the amount of water you have to evaporate it. So that is 98.7%. Okay, most of the water has to be evaporated to make this one critical. Assuming that the deuterium fusion reaction, the fuel consumption is 0.151 gram per megawatt a day. Find the energy release in joule per kilogram. Then by what factor is the value larger or smaller than that of for fission? If the high water cost is $100 per kilogram, what is the cost of deuterium per kilogram? C. Noting 1 kilowatt hour is equal to 3.6 times 10 to 6 joule. Find from A and B the thermal energy cost in cent per kilowatt hour. First, we just need to do some unit conversion. So here we have a gram per unit of energy. We want it to be converted to unit some energy per unit of mass. Okay, mass per unit energy, then energy per unit mass. So we just take the reciprocal of this value, okay, 1 over this 0.151 gram per megawatt a day. Okay. Then we get this value. Then we also get the reciprocal for this unit, okay, megawatt a day per gram. Then we convert the megawatt a day to joule. Okay, convert the megawatt a day to joule and convert the gram to kilogram. And for megawatt a day, 1 megawatt is 10 to 6, then times 24 times 3600 for the seconds. Okay, so this is watt times seconds, so we can convert it to joule. Then gram to kilogram, that is 1000 factor. Then we get this value. So that is the amount of energy released in joule per kilogram. Okay. Next, we need to make a comparison for the fuel efficiency. Okay. And for 235, for the fission, we use 235 as a representative fuel. We know that 1.3 gram of 235 can produce 1 megawatt a day. Okay. So therefore, for this fission, this value is 1.3 gram per megawatt day. Okay, and this value, how to calculate this value is presented in example 6.5 on page 111. This value was also introduced when we solved the example 22.1. Okay, and also some of the previous homework problem. So we can use this value directly. So we use this 0.151 over 1.3. So we get this factor. Okay, we get this factor, then that is finished. Or you can have another conclusion. So this is to produce the same amount of energy, so the fusion fuel will be 82 times smaller than that of fission. Okay, so means the fusion fuel will be more efficient. Problem B. If high water cost is $100 per kilogram, then what is the cost for deuterium per kilogram? So this problem is easy, and you think that in this way. So the head water contains both the deuterium atoms and also the oxygen atom. Then when we burn the deuterium in the fusion reactor, we only use the deuterium. Therefore, we are going to remove this oxygen. We'd like to just know if the high water cost is $100 per kilogram, then what is the cost for the deuterium? So we use the 100. That's dollar per kilogram times the total mass of the deuterium over the mass of total mass of the high water molecule over the mass of the deuterium inside the same molecule. Okay. Then you get 500 per kilogram because only a small percentage of the mass is deuterium. Okay. Problem C. We'd like to know the thermal energy cost in cents per kilowatt hour. So from the problem A, we know that to burn 1 kilogram of the fuel, it will produce this amount of joule. Okay, this amount of joule. We'd like to convert this unit to kilowatt hour per kilogram. Okay. So we use this joule per kilogram divide joule per kilowatt hour. Then we get we just convert this value to kilowatt hour per kilogram. Okay, so that we can make this unit to be consistent to what is requested. Okay. So it means that to burn 1 kilogram of the fuel, it can produce this amount of kilowatt hour. Okay, this is also thermal energy, as shown here, thermal energy cost. Then 1 kilogram of the fuel, the cost is $500. Okay, $500. So $500 per kilogram. Divide this value. Okay, divide this value. Then you get the dollar per kilowatt hour because the kilogram will be cancelled. Then you have the dollar in the numerator left and the kilowatt hour in the denominator left. So the unit will be dollar per kilowatt hour. Okay, so result will be dollar per kilowatt hour. Then we convert it to cent. Okay, convert it to cent. So this small value, cent per kilowatt hour. So it means that from this rough estimation, the cost for fusion reactor will be very low. This is the last problem in this lecture, 27.4. Assuming an annual need for 4% of uranium-235 fuel of 50 tons per power reactor, how many reactor years of operation can be achieved with 20 tons of 90% uranium-235 when downblended with 0.7% natural uranium? So for this problem, it means that for a power reactor to operate 1 year, it will consume 4% 235 fuel of 50 tons. Okay. Now we have 20 tons of 90% of 235. We want to mix this 20 tons of 90% 235 with 0.7% of natural uranium. The total mass is unknown. We want to use this 90% and 0.7% of uranium to make the 4% of the fuel. We want to know how many tons of 4% of this fuel can be produced. Okay, can produce. And here there are many different ways to solve this problem, and here I'm going to show how I solve this problem. We are going to set the x, okay, set this x to be the amount, to be the mass of the natural uranium, okay, mass of natural uranium. So we have 20 times 0.9. Okay, 20 times 0.9, that is the pure 235 from this highly enriched uranium. Okay, 20 times 90%. That is the total mass of the 235 from the HU, highly enriched uranium, plus the X, that is the total mass of the natural uranium, times the 235 enrichment, that is 0.007, is equal to 20, that is 20 tons, plus this X times 4%, because the product is 4%. So everything here, so the total uranium-235 from these two streams is equal to the total uranium mass of the product. Then we solve the X, that is this value, 521 tons. And pay attention that this X is the total mass of the natural uranium. So the total mass of the product will be this X plus 20 tons. Okay, this X plus 20 tons. So this is the total mass of the product, 4%. Each reactor year will consume 50. So we divide by 50. That is 10.8 reactor years. That's it. And for this lecture, I listed 9 problems. If you have any question regarding other homework problems, you can either contact the TA or contact me through Teams, through Microsoft Teams. And we are very happy to explain that to you. Thank you.